Hi, chemistry students. This is your lesson on mole-to-mole stoichiometry problems. You likely have some guided notes. Please be sure to pause the video as you need to write down the examples we will be doing. So this is a sign that is on a lot of chemistry teachers' doors. Chemistry is like cooking, just don't lick the spoon. If you are a chemist who needs to synthesize material, make materials, you want to be sure you can predict how much product you can provide to your client. Fortunately, this is as simple as following a recipe, or as, for example, figuring out how much cheese and how many crackers you would need for a cheese and cracker sandwich. In a chemical equation, the ratio of coefficients, or the mole ratio, can be used to make this prediction. However, we're going to use a special term called stoichiometry to talk about this. The word stoichiometry is derived from two Greek words, one meaning element and one meaning measure. Now, in the process of mixing elements during chemical reactions, the amount of the reactants determines the expected amount of products. And this is often true in cooking as well. So this is really no different than following a recipe and scaling it up and down to the amount of product that you want or the amount of reactants that you need. So we're going to do what I would say is a proof of method exercise. We're going to do something that you're very familiar with so you can understand that the method we're going to teach you with stoichiometry using ratios and dimensional analysis actually does work. So I have a recipe here for making a sort of a traditional cheese and cracker sandwich with maybe some Ritz crackers. You're hungry? You go to the refrigerator, you get one slice of cheese, you fold it up real good, and then you go to the cupboard and you get two crackers, and you put the cheese in between the crackers, and you get one sandwich. So you can see this is the recipe that looks a little bit like a chemical reaction here. One cheese plus two crackers gives us one sandwich, and there are a whole bunch of ratios here. So there are a lot of ratios between the cheese, the crackers, and the sandwich. So like, for example, one slice of cheese for every two crackers to make the sandwich, or two crackers for one sandwich, or one sandwich, you need one slice of cheese. And you can also have the inverse of this when you're doing the dimensional analysis. So we're going to do a proof of method. And so if you're like, oh, okay, I've got my recipe for making one sandwich, but I'm really hungry. I want 5 sandwiches. So how many crackers would I need to get out for 5 sandwiches? Now, I know you can do this in your head. That's not the point of this. The point of this is to prove the method. You know it's 10 crackers to make those 5 sandwiches because you're very familiar with making cheese and cracker sandwiches. But let me show you the stoichiometric way. So you're going to start with a given, all right, which is sandwiches. And the given always, this is the number and the unit that comes from the question that you're trying to answer. And then there's a want. How many crackers do I need? And the want is the how many, okay? Now you're going to use a ratio from this balanced equation since this is only for one sandwich and you want 5. And the ratio between crackers and sandwich is 2 to 1. So we set the ratio up like this, and remember, whatever's on the top is multiplied, whatever's on the bottom is divided. And you want to set it up so what's on the bottom cancels what's on the top, the unit does, and the unit that's on the top of the ratio is exactly what you want. So the correct ratio to pick from this would be 2 crackers for every 1 sandwich, so 5 times 2 gives us 10 crackers. So this method using the ratio works. It gives you the answer you would expect. Okay, let's do another one just to get some practice. How many sandwiches from 14 crackers? And again, remember, we're going to use the same thing when we start talking about chemical reactions. We're going to have a balanced recipe. We're going to have a balanced chemical reaction. And we're going to then go up and we're going to look at the problem and find the one with the number. So 14 crackers comes right down here. And then we're going to find the how many or how much statement. And that's what we want. So we want to figure out how many crackers to make this many sandwiches. 14 crackers make how many sandwiches. So I go to my cabinet. Here's the problem. I got 14 crackers. And I got lots of cheese. And I want to know how many sandwiches I can make. I only have 14 crackers. So I'm going to get the ratio here. I'm going to get the ratio of crackers to sandwiches, which is 2 to 1. Now the question here is, do I multiply or divide? And I'm going to use the ratio 1 sandwich is 2 crackers. So again, 14 crackers, and the crackers here will cancel. The sandwich will go across. 14 divided by 2 gives us 7 sandwiches. Notice the unit in the denominator cancels, the unit in the numerator is the one that carries through. So 14 divided by 2 gives you, I could make 7 sandwiches with those 14 crackers. Okay, so hopefully we've proved that method works. Now I want to talk to you about a term that's going to be important later on. It's called the limiting reactant. Now the limiting reactant or limiting reagent is a reactant in a chemical reaction that determines the amount of the product that is formed. And practically speaking, it means it's the reactant that's going to run out first. It would be lovely to think you would have exactly the right amount of cheese and the exact right amount of crackers, and that at the end there would be no cheese left and no crackers left. But we know practically that doesn't always happen. So let's look at an example where we can illustrate this idea of a limiting reactant. So if I had 4 slices of cheese and 10 crackers, what is the limiting reactant? And you want to show a calculation that justifies that, okay? So here are our 2 ratios. If we had 4 slices of cheese and we have the ratio of 1 sandwich for every 1 slice of cheese, 4 slices of cheese could make 4 sandwiches. If I went to my cabinet and found 10 crackers there, I see that using the ratio of 1 sandwich to 2 crackers, I could make 5 sandwiches with the 10 crackers. However, I am going to run out of cheese at 4 sandwiches. So since the cheese makes less, it is the limiting reactant. Okay, so with 4 slices of cheese and 10 crackers, what's the limiting reactant? Cheese, because at 4 sandwiches, I run out. How many sandwiches can I make? 4. The crackers run out. They're called the reactant in excess, or the excess reactant. And we would still have 2 crackers left over after we made our 4 sandwiches, right? We'd have 2 left and we'd have to just eat them plain with no cheese in between, or just put them back to the shelf once we got more cheese we could use for making cheese cracker sandwiches. So the limiting reactant is the one that runs out, that makes the fewer amount of sandwiches, and the reactant in excess is the one that does not run out. Okay. So let's talk about this in terms of chemistry. We've talked about it in terms of sort of a recipe in cooking. Remember, coefficients represent particles and moles in a balanced chemical reaction. The coefficients do not represent grams. They have to be converted. And just look at this equation for the synthesis of water. Note that 2 molecules of water plus 1 molecule of oxygen gives us 2 molecules of H2O. Mass is conserved. We can see this within the particles. We're just rearranging things. Similarly, we could make molecules into moles because they're proportional. So 2 moles of hydrogen and 1 mole of oxygen gives us 2 moles of water. Notice that the number of moles matches the coefficient. The mass does not. 4 grams of hydrogen is the weight of 2 moles of hydrogen. 32 grams of oxygen is the weight or the mass of 1 mole of oxygen. And 2 moles of water is equal to 36 grams of water, okay? But you notice 4, 32, and 36 do not match the coefficients. The coefficients match moles or molecules. So that's why in doing stoichiometry, we have to use mole ratios. So again, here is the formation of water, the synthesis of water, and there are a lot of mole ratios we could use between them. We have 2 moles of H2 for every 1 mole of oxygen, or 2 moles of H2 for every 2 moles of water, or 1 mole of oxygen for every 2 moles of water. These are our mole ratios, just like we had cheese and cracker ratios in the previous example. So let's try an example, one that involves a chemical equation. It says, how many moles of oxygen gas are needed to make 15 moles of H2O? Now, you can see from the problem, we have 15 moles of H2O, and we want to find how many moles of water. Now, one thing we're missing here is we need the recipe. Here's the recipe for making water. We need to have hydrogen and oxygen to give us water. Here is the ratio, 2 to 1 to 2. And the question says how many moles of oxygen gas are needed to make 15 moles of water. So if somebody said, I need you to make some water for me, I need 15 moles of it, how many moles of oxygen would you have to get? So the given is 15 moles. The want is moles of oxygen. And then to convert, we're going to have to just use the ratio. Well, the ratio here is just 1 to 2. So 1 oxygen for every 2 waters. Notice how water is on the bottom, H2 is on the bottom, H2 is here. We can cancel those. The thing that carries is in the numerator. It's the oxygen. So it's going to be a division, okay? All right, it's going to be a division. So 15 divided by 2 gives you 7.5 moles of water. Okay? And I want you to see that this is the same ratio. This was a recipe for making 2 moles of water. We wanted to make 15, just like you would scale up a recipe if you needed to make more. And again, 1 to 2 is the same as 7.5 to 15, right? 1 to 2, 2 is twice of 1. If you multiply 7.5, you get 15. This ratio is the same. It's just scaled up to 15 moles of water. Okay, let's try a few more examples with a little more complicated one, because this one, it's a 1 to 2. You probably could guess right. It probably makes sense. But what if it's something that's a little more complicated, like 3 to 2, for example, and it's very easy to get confused about which one should I multiply and which one should I divide by. So here is a single replacement reaction of aluminum reacting with copper chloride to give you aluminum chloride and copper. It is balanced with 2, 3, 2, 3. So you see all these ratios that are possible from the balanced equation are 2 to 3 ratios, or 3 to 3 ratios, or 3 to 2 ratios. And it can get confusing when you're doing conversions, like maybe I want 7 moles of copper or 5 moles of copper, to know how many of these other things you're going to need. Am I going to multiply by 3 or divide by 3? So let's try a few. Here's example number 2. How many moles of aluminum will react with 6 moles of copper chloride? Again, same process. We're going to, first of all, find the given and find the wanted. So the given in the problem is the one with the number, 6 moles of copper chloride. And the wanted is how many moles of aluminum. So how many moles of aluminum? Now, we can see there's a ratio here between aluminum and copper chloride. If we wanted them to react exactly, it's a 2 to 3 ratio. So we're going to have this 2 to 3 ratio here. Again, to arrange it correctly, because we want to get moles of aluminum, we're going to put aluminum on the top. And again, we're just pulling this from the balanced equation, and the copper chloride on the bottom, because that will cancel the given. Whatever is given, that coefficient and that thing from the equation is going to go on the bottom, and what we want is going to go on the top. So now we know that it's going to be 6 times 2 divided by 3, which is 4 moles of aluminum. So if we had 6 moles of copper chloride, we would need 4 moles of aluminum to react with it completely. And again, if you look at this, it's a 2 to 3 ratio, and what we figured out is that's the same thing as 4 to 6, and that does make sense. Okay, let's give another example. How many moles of copper will form from the reaction of 3 moles of aluminum and excess copper chloride? Now, this is trying to throw something out at you. You see 3 things in here. How can you have 3 things in a ratio? But you'll notice here, excess copper chloride is a distractor. It's to try to confuse you. It's just like the crackers. We have plenty of copper chloride. We don't have to worry about it running out. But we know that we're going to run out with 3 moles of aluminum. So whenever you see and excess, or the excess reactant is this, then you're going to cross it out and ignore it and recognize that a ratio can only have 2 things in it, and it's going to be the copper and the aluminum. We don't care that there's extra of this other reactant. So again, let's set it up with the given and the want. So from the problem, it's given with the number, 3 moles of aluminum, and the wanted is how many moles of copper. So if I start with 2 aluminum and I have tons of my copper chloride, I'm soaking the aluminum with copper chloride so that all of the aluminum reacts. How many moles of copper would I get? So we've got to set up our mole ratio. If we do that, the mole ratio is going to be 3 coppers to 2 aluminums. Why? Because we're going to cancel aluminum in the denominator with aluminum in the given, and the thing on the top in the numerator is what carries through. So it's going to be 3 times 3 divided by 2, which is 4.5 moles of copper. Now, does that make sense? Okay, whoops. Let's look at this. So does that make sense? So 2 to 3, is that the same thing as 3 to 4.5? Well, it is. It's the same ratio. Let's look at another one. How many moles of aluminum chloride will form from 0.25 moles of aluminum? Now, let's look at the ratio here. It's 2 to 2. This should be an easy one, but we're going to set it up the same way. 0.25 moles of aluminum, and here's our mole ratio, which is 2 to 2, so 0.25 moles of aluminum chloride. So if I start with 2 moles of 0.25 moles of aluminum, then I'm going to get the same number of moles of aluminum chloride. Okay? All right, let's look at one more example. How many moles of alumina are needed to form 7 moles of copper? So it's a little harder to sort of do in our head. So this reaction has us forming 3 moles of copper. It's a recipe to make 3, but we want to make 7. So we need to know how many moles of aluminum that is. It's a 2 to 3 ratio. How do we figure that out? Okay, again, the given is 7 moles of copper. And the ratio we're going to use is 2 aluminums to 3 copper. So it's going to be 7 times 2, which is 14, divided by 3. Again, note, the thing that is here we put on the bottom because we want copper to cancel. The thing that we want we use in the numerator because that's what we want. So 7 times 2 over 3 is 4.7. And some of you may be asking about significant figures. Now, mole ratios are exact numbers. 2 is exactly how many aluminum we need to react with 3 coppers. So we don't take the mole ratio as part of our significant figure calculation. We do look at what we're given here at the beginning, like 7 moles. That's 2 significant figures, and because that's a certain amount of copper we're given. The ratio is our exact numbers, so they don't figure into significant figures. Since this has 2 and it's a multiplication, this will also have 2. So 7 times 2 divided by 3, I think, is like 4.66666, but we'll round it to 4.7. And that is your lesson on doing mole-to-mole stoichiometry. You will have an exit ticket on this if you're in my class, and a lot of practice problems. So keep working. Thanks very much.